there are really two kinds. There's the A and B models. So we'll start off by describing the B model. So normally, if you read papers about the topological strings, people will insist that they only make sense in complex dimension 3, Calabi-Yau threefolds, at least in the physics literature. But there's nothing stopping you studying them in any complex dimension. They're perfectly well defined. So the B model we're going to consider it on a Calabi-Yau manifold. X is complex dimension, we'll assume to be odd. Ultimately, what we'll find is that the usual three-dimensional version, well, that's of course the usual topological string, but if I study this in a Calabi-Yau fivefold, that's very closely related to type 2B string theory. So what do I mean by the topological B model? So I'm not going to focus on the worldsheet so much. I'm almost entirely focused on branes and the supergravity model living on the target. So I'll first discuss the branes. Suppose I take a complex submanifold. Of dimension k, complex dimension k, then there is a B brane living on it. And more generally, I could consider this submanifold together with a vector bundle on it. But that's really equivalent, at least locally, to having a stack of n of these branes. So, for example, most of the time, we're going to consider some CK inside of CD. Flat case, so I just have some complex linear subspace inside this d-dimensional space.
Where do you want the dimension to be?
Some things work in the even dimensional case too, but you have to do some very strange things to write down the open string field action in the even dimensional case involving the first Clifford algebra, and I didn't want to get into that. So what are the open string states? So the math definition would involve words like derived categories and X groups and things like this. But if we just focus on this case of a linear subspace, it's actually very simple. From states connecting CK with itself, are the states, which is the Dolbeault complex of CK. And then I join D minus K odd parameters. So remember that the Dolbeault complex is just functions on CK. I join these K odd parameters, dz bar 1, dz bar K, with differential d bar is some dz bar I, d by d, z bar I. One can compute the open string states connecting any two complex submanifolds, no matter how they're arranged. Maybe I'll do some examples later. But
what's the commutation property between epsilon and dz bar?
They supercommute. Okay. So if we have n branes wrapping CK, well, we find the same answer, but the usual picture where I could have a string ending on brane I and brane J on the other side, so I find matrices. That's our GLN. So I don't know if people are familiar with Witten's famous paper about open string field theory, in which he argued that the space of states of an open string carries a structure known as a differential graded algebra structure. So we should expect this space to have a product and a differential. So this, it does. The product is the one we just discussed with Latch, satisfying these relations. It's obvious. And the differential is d bar. It has one more piece of data. It also has an integration map, assuming we look at forms if we look at forms, which decay rapidly at infinity, it's going to call it trace. Also a trace map. Which sends a matrix whose coefficients are in this ring to the integral. Now here we're going to use a Berezinian integral. These epsilon i's, they're odd variables, so we can do a Berezinian integral over those variables. So it's ck slash d minus k of dz1, dzk, d epsilon 1, d epsilon d minus k of trace of A. Make sense so far? So in Witten's paper, what he said was, he said that any time you have some space of open string states, it should have this kind of structure, and that one can write down an open string field theory built from this vector space with an action function built from this data. We take the fields to be not the original space here, but it's partly reversed version of that. Or A, I'm going to curly A for this algebra because I'm tired. And the action Okay. So this is what the kind of Chern-Simons action Witten wrote down that one expects any open string field theory to have.
What's pi?
Pi is parity reversal. So in this algebra, fermionic elements of this algebra will correspond to a bosonic field. So for example, in this open string field theory, because of this parity reversal, you can take epsilon 1 and up to epsilon d minus k these describe d minus k bosonic scalars in the open string field theory. And what they are, of course, they describe the fluctuations in the normal direction.
Are the vectors in this complex the states in the topological string theory?
These are the states in the topological string theory, but I want to argue that they are related by some Q-cohomology procedure to the states in the physical string theory.
And this differential operator, is that related to the supersymmetry of the B model? Del bar.
This del bar, how do you mean the supersymmetry of the B model? It's like the BRST operator on the open string states of the topological B model. And if to relate it to the physical string, I expect it to be related to the sum of the BRST operator of the physical string with some supersymmetry.
So pi is a new algebra derived from here?
Pi is not an algebra because parity reversal doesn't change. If to have an algebra, the product of two bosonic things must be bosonic, and that doesn't happen anymore. So reverse parity. So pi is just a vector space on which there's an action.
So what does alpha times b bar alpha mean?
Oh, I suppose maybe I should have put a pi here. You take a degree 0 element of here, or an even element of here, view it as an odd element of A, and then apply this formula.
So we first convert to A, then do your manipulations, and then you convert back to...
Yes, then integrate, you get a number. But I hope that, this is one example why it's kind of clearly the right thing. On the open string field theory, we need to have these d minus k scalars. There they are. We also have a gauge field. If I take some dz bar I, some quantity like that, will give a bosonic element again, because it's omega 0, 1, it's fermionic in this algebra. It will give me a bosonic element of the space of the open string of the space of fields. And this bosonic element is, of course, it's part of a gauge field. Okay, so let me, does that make sense? So I'm more of a fan of the B model than the A model. I'll discuss the A model in a bit later. So what I want to do, now we have this on the board, is I want to explain how I expect this to be related to the physical string so that we can play the usual games in the physical string, in this topological world, and see what happens. Okay, so let's consider type 2b string theory on R10. So let's say S plus is the 16-dimensional chiral spin representation. Then the supersymmetries of type 2b are two copies of this guy. Now, we're going to be interested in a kind of a twist of this. So we're going to take some supersymmetry and take Q cohomology using that supersymmetry. So I have to specify what supersymmetry I want to consider. So the feature I want to preserve, well, there's nothing, we're in such a high dimension. I mean,
is there a reality condition on S plus plus S plus?
I'm not going to worry about that because that's a signature dependent condition and I want to work in Euclidean signature.
I mean, there should be 32 real supercharges, right? And this seems like 32 complex.
Right, but we're never going to see Q bar. We're only going to see Q. So, I mean, when you work in perturbation theory, there's nothing. You can always just complexify everything, and reality conditions don't play any role. Because you can. That's all we're doing. So you're right that in the Lorentzian signature there is a reality condition, even on one of them. But I'm not going to worry about it if we don't care about it. So normally people would like to study topological twists. So to consider a topological twist, you might start off with some homomorphism from the Lorentz group, in this case spin 10, to the Orr symmetry group. Here we have no chance of finding such a thing because in perturbative string theory, the Orr symmetry group is O2, and non-perturbatively it's broken. SL2 OR, and non-perturbatively becomes SL2Z, so we have no chance of finding such a homomorphism. So we're not going to aim for a topological twist. What we're going to do instead is break Lorentz symmetry. We're going to look for a supercharged invariant under some subgroup. So we'll consider, I mean, there are many choices here. So the choice I'm going to make, which matches this, SU5 inside of spin 10, then you can check that there are two supercharges. Say Q1, Q2, which are invariant under SU5. And if we allow ourselves to use the perturbative Orr symmetry group, we can always rotate one into another. So there's really only one of them. There might be some subtle non-perturbative effects that I'm not going to worry about. So we'll pick one. And then we're going to twist using this. Okay, so think I have to say something about what this means, because this is not something one ordinarily does to a string theory. It's something one might do to a supersymmetric field theory, so it's might seem a bit worrying to try to do it to a string theory. So let me first explain what happens with branes, because that's closer to the most familiar situations. So if we use one of these supercharges, then a brane is preserved by Q, certainly a brane embedded linearly, if it lives on a complex subspace. So twisting just means for branes which are preserved by Q, we add Q to the BRST operator of the open string fields. So we're going to ask what happens with closed string fields. It gets a little, I won't spend much time on this because it might seem a little abstruse, and I don't want to lose people.
How does Q act on the open string fields?
Just by, if we take the low energy open string fields, there'll be some supersymmetric gauge theory in some dimension. This will be one of the supersymmetries on that. And you can determine which one by symmetry constraints.
I mean, in terms of the algebra?
Oh, what I want to claim is that this algebra is the Q cohomology of the open string fields of the physical brane.
Okay.
So that the d bar operator there contains some hint of Q, because choosing the d bar as a complex structure, the complex structure is related to Q because Q picks out an SU5 inside of SO10. Well, maybe I won't spend too much time on. So for closed string fields, kind of the fancy way to say it, Q is an element of the local supersymmetries which give ghosts in type 2b supergravity. And twisting in this way means we're working, because it's a fermionic symmetry, and ghosts are fermionic, this becomes a bosonic field. So we're working in type 2b, where the superghost has an expectation value given by Q. So as I said, this is the kind of super fancy kind of conceptual way to try to think about how this relates to the physical string. But in practice, you look at this, you might look at the states of the physical string, the supersymmetry acts on those states, and we take the cohomology. to concretely, we just add Q to the BRST operator of the closed string states. So one more thing you might wonder, well, I've talked about branes and the low energy supergravity. What about the string itself? Again, the only way I know how to think about this is in some kind of fancy language like this. Yes, the superghost is bosonic. Well, this vector space of superghosts is a bosonic vector space, and it's the space of spinors. So the superghosts are bosonic spinors. And
Q implements a supersymmetric transformation, so it should be fermionic.
It's a fermionic symmetry corresponding to a bosonic ghost.
Oh, so you take phi of that.
Yes.
Okay.
Yeah. So you can get yourself tied up in knots in this stuff. Sorry. So what happens in this string? So my understanding is that the superghosts should live inside the states of the string. There'll be certain bosonic Ramond-Ramond states. So all we're doing is we're working in a very strange Ramond-Ramond background for the physical string, where I've taken my string worldsheet and put a bunch of punctures on it. Kind of sum it up overall ways of putting punctures on it, and each puncture I put a Ramond-Ramond state given by Q. That's, of course, unfortunately, it's very hard to make it to understand string theory in a Ramond-Ramond background, so that doesn't really help us. Okay. So the conjecture, which allows us to, forget about silly abstractions and kind of do some computations, is that the twist of string theory of type 2b just is the topological string. This SU5 invariant twist of type 2b and OR10 is equivalent to the topological B model on C5. So the reason I like this is, well, if we believe this conjecture, then we can do computations in the physical string. It's very hard to compute anything in the physical string. We can compute them in the topological string instead, and the computations are much easier. And that's particularly true for the case of for supergravity. Supergravity in 10 dimensions is kind of hard to deal with. Over here, there's some closed string field theory, which turns out to be a bit easier to deal with. You can, in principle, compute with. So let me write down the dictionary for how I hope this might go. Conjecture it goes. So the easiest part is branes. So in the physical type 2b, I have branes with an even-dimensional world volume. So I can take the d2k minus 1 brane on some copy of ck And this will become the corresponding B-brane on the same space. And you can check, for instance, that this brane is supersymmetric, as I said, if this is a holomorphic submanifold, which is the condition under which the B-brane exists. Now, what's next? We can consider open string states connecting two branes.
Is it important to have R10, or can you replace it by some other kind of dimension?
You could replace it by a Calabi-Yau fivefold, because you need a covariant constant spinner, one covariant constant spinner. So if I take the open string states, over here, where I add on whatever might be your ST operator is, I add on the supersymmetry conjecture that this is equivalent to, they have the same cohomology as this space over here, the space of open string states between two branes, just with the d bar operator. The holomorphic twist of the low energy theory on the brane this should correspond to the open string field theory we just discussed. Where the fields are this algebra, but made fermionic. Okay, and of course there's many more things to check.
This open string field theory is supposed to be quantized in some sense, or do I take the classical?
Over here? Well, just like in the usual physical string, in the B model, it's not being proven in full generality, but it's expected that you can always quantize the coupled open-closed string theory together. You may or may not be able to decouple them.
I mean, you asked for the open string field theory.
Yes. Well, the open string field theory by itself is sometimes anomalous. Sometimes cannot be quantized. But you wouldn't do that in a physical string either. You wouldn't talk about 10-dimensional Yang-Mills as a quantum theory. So you want to, UV completion is, you want to include string theory.
So it's supposed to provide me with some diagrams in the.
Yes. Yeah, absolutely. I mean, in the cases, suppose I considered a D3 brane and corresponding thing here. You expect that this will tell you about some 1/16 BPS operators. It's 1/16 BPS because, I mean, if you think about SU5 invariance, and it will imply 1/16 BPS.
I'm supposed to take all the loops in this theory, and
yeah.
Or when I compute a scattering amplitude.
Yes, that's right. Although in general, this theory is much simpler for the reason that typically it's much easier to compute things between supersymmetric operators, and it often stops at one loop by. There's various arguments by Seiberg and so on that for supersymmetric operators you don't find any higher loop corrections in many cases. So these theories are often one loop exact and often quite easy. Okay, so there's lots of things of this I wanted to try and explore. This kind of thing is the main topic, of course. So I'm going to talk about the type 2A, different supersymmetries, how do other supersymmetries manifest in the topological string, T-duality, S-duality, M-theory, if we get there. But before we get any further, you kind of want to have some idea that actually we're on the right track, that these statements are actually true. So I spent some time talking about twists of holomorphic twists of supersymmetric theories last year sometime. And we saw examples like this. So I can quote some results which show that these things are really true. So well, here's some notation just to stop things being too cumbersome. We'll denote the theory whose fields are that is a theory which lives in a brane in the topological string. We'll call this as holomorphic Chern-Simons on CK/5 minus K. This is justified by noting that the action we write down for this is a holomorphic Chern-Simons action. It looks like this form. So the action looks as this holomorphic Chern-Simons form, and it is open string field theory action. So we'll call it holomorphic Chern-Simons on CK/5 minus K. There's a following very nice result of Laurent-Beaulieu. So consider the SU5 invariant twist of maximally supersymmetric gauge theory on OR10. Then this is equivalent to holomorphic Chern-Simons on C5. Okay. So what he did in this paper, you write down the field content, there's some gauge field and some spinners. You arrange them into SU5 multiplets. You get rid of some things that disappear under Q cohomology, and you find exactly this. So this checks the result for the D9 brane. So the D9 brane in the physical string corresponds to the D9 brane in the topological string. Okay, so this is the first evidence that really this proposal is correct. But now you can ask, well, it turns out that by dimensional reduction, you find all the other cases followed by dimensional reduction. So if we reduce 10-dimensional supersymmetric Yang-Mills to 2K dimensions, what we find is the theory living on a D2K minus 1 brane. At least the low energy theory living on a D2K minus 1 brane. So to see if this correspondence works for other branes, what we have to do is just apply dimensional reduction on both sides. So we have to check that dimensional reduction of holomorphic Chern-Simons theory here to lower dimensions gives us what we said it did. So if you reduce holomorphic Chern-Simons on C5, CK, what do we find? Well, for holomorphic Chern-Simons on C5, the fields are, I take functions on C5, I join dz bar 1 to dz bar 5, tensor G on n. And all we do is we make our fields in translation invariant in some number of complex dimensions. So make the fields constant in 5 minus k dimensions. And we'll, so dz k plus 1 up to dz5, z bar 5, we'll replace these, we'll rename them, we'll identify with epsilon 1 f's up to epsilon 5 minus k. And then for fields are constant in a bunch of directions, we're left with a theory in lower dimensions, including the correct number of these fermionic variables. Which is the correct thing. So this argument tells us that d2k minus 1 brane in the physical string really matches up with a d2k minus 1 brane in the topological string.
How do you apply this argument to a general Farabi field?
That's a good question. I suppose you would argue that everything is determined by what it is locally. Probably you want to say that locally, whatever you find in any dependence on the metric in the physical string is Q exact with a supersymmetry. So we can apply this argument locally. Something like that. But I must admit I don't have a very solid argument in full detail for the curve case. Okay, any other questions? Let's see, so the other, I'm stop it a few minutes, but some of the more complicated aspects of the story, like the story with branes is much easier in some sense than the story with closed strings. So I might leave the story discussion of closed strings till next time when the audience is much smaller. But I'm maybe spend a few minutes talking about type 2A. So to understand type 2A, we need to understand the topological A model. So let's consider R2n and view this as a symplectic manifold. with some two-form some non-degenerate two-form. So we're going to find the topological A model on this manifold. So branes are given by Lagrangian submanifolds. So we're mostly going to be considering the simple case when these are linearly embedded. They're even dimensional. Or, sorry, middle dimensional. Given a brane, you can consider the space of open string states from a string ending on that brane. That you just find that they're the algebra of differential forms on this manifold. Now, there's a simplification we're using. If we were in some more complicated geometry, there might be non-perturbative effects which make the space of open string states much bigger. But we don't have that here. So the open string fields the same kind of argument is and the action is the I'm going to assume that n is odd for simplicity. The action is the Chern-Simons action. Okay, so it's pretty much parallel to the closed string case, except the algebra we find is just this de Rham algebra instead of the Dolbeault algebra. And in the closed string case, we also have these odd variables, which we don't have here. Sorry, in the B model case. So I'm going to consider one more variant. What we're really going to be interested in to describe type 2A is something slightly funny, which is an A model in some directions and a B model in other directions. So the claim is that a twist of type 2A is the topological string theory on OR2 times C4, which is an A model on OR2 and a B model on C4. So we can write down some things like we did before, some kind of dictionary. So the A model, so this is an SU4 invariant twist. A particular one. So the branes in type 2a have an odd dimensional world volume. So you have D2k branes. And what these two correspond to is, if you think of what are the branes here, you could have a complex submanifold of C4 that will be even dimensional, and a Lagrangian submanifold of R2, which is a straight line. So these should correspond to R times CK inside of R2. And we expect in the same way that the twist of the open string field theory so that if I take the twist, which comes from the supersymmetry we've chosen of the theory on the brane and the physical string, we expect that this becomes the field theory on the brane of the topological string. And actually, the same argument applies because here we have some maximally supersymmetric theory in some odd dimension, which is also obtained by reduction from 10 dimensions. And you can check that the theory living here is obtained by reduction from holomorphic Chern-Simons along an odd number of dimensions. So this does indeed hold. Sorry, one last comment is that the pictures for 2a and 2b I've described, they're T-dual. There are T-duality results in the topological string, which says that the A model on R cross S1 is equivalent to the B model on C star. So this implies that the mixed A-B model on R times S1 times C4 is going to be equivalent to the B model on C star times C4. And here we have 2A, and here we have 2B. So the setup we've described is indeed compatible with T-duality as you would expect it to be. Okay, stop there.
Is there something really special about the 4 here? Like you might have R4 plus 3.
So I was going to talk about things like that next time. You can always take any two B model directions and turn them into an A model direction. There's some supersymmetry which will always do that for you, it turns out. So by using a different supersymmetry, I could describe it as the A model in R2 and R6 times C2, or on R10. And the B model, could be B model on C5, A model on R2 times B model on C6, or A model on R8, B model on C.
What's the general structure of, what's the most general manifold I can write down? So
Oh, that's a very good question with this property. Probably you'd want these to be part of some kind of foliation, like a codimension 8 foliation with the transverse holomorphic structure, and something like that. See what I'm saying?
what does it mean in terms of vibration? What is fibered over what? Which part?
Oh, this part will be fibered over this part.
So there will be some two-dimensional symplectic manifold fibered over a Calabi-2.
Calabi 4.
Yes.
Yes, that's right. Yeah. Or also maybe 6-dimensional Calabi manifold fibered over Calabi 2 will be another example. the example you normally consider in the physical string.
What is the total manifold called in this case? Is there some-
I don't know. I don't.